In this video, we're going to talk about similarity with right triangles. So the right triangle altitude theorem states that if we have an altitude drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So if we take a look over here at this image that is on this slide, BD is an altitude. An altitude is just a perpendicular line in a triangle that passes through the vertex of the triangle. So BD is an altitude because it does pass through vertex B. Vertex is one of the points of the triangle, A, B, or C. And it is an altitude also because it's perpendicular to the side of the triangle it's drawn to. As you can see, when it intersects side AC of the triangle, it forms 90-degree angles. So it is a perpendicular line through the vertex of the triangle, through one of the vertex points of the triangle. And the way that you can tell that the triangles are similar to each other is because the big triangle and the two smaller triangles that are formed by the altitude are all right triangles. So they all have a right angle, and all right angles are congruent to each other. And since each of the smaller triangles is inside of the big triangle, there's a shared angle between each of the small triangles and the big triangle. And when we have shared angles, that means it's congruent to itself by reflexive property. So if there's two congruent angles, the shared angle and the right angle, we have AA, which makes the triangle similar. When you're approaching questions like this, it's really important to also recognize that the two smaller triangles are not facing the same way, not oriented the same way as the big triangle. If we want to see what corresponds to one another in the triangle, what sides match up, what points match up in the two triangles, we should redraw the triangles so that they're all facing the same direction. So I'm going to do that now. I'm going to draw them in size order. Big triangle, medium triangle, small triangle. Now, the labeling of the big triangle doesn't matter. It's just I want to put the right angle in the same spot in all of the triangles because we're trying to orient them the same way. So it makes sense that the right angle would be in the same spot. So in the big triangle, the right angle is at B, so I'm going to put B there. But it doesn't matter where I put A and C for this first triangle, the big triangle. It does matter for the other two triangles because they're going to be based off of the big triangle. So I'll just put C over here and A over here. Like I said, it doesn't really matter for this one. It will matter for the other two triangles. So for the medium triangle, and I know they look the same size here, so I'll just outline the one that I'm referring to as the medium triangle as this one in purple. The right angle is at D, so I'm going to put that there. And we talked about how since this triangle is inside of the big triangle, there's an angle that it shares with the big triangle. And that angle would be angle A. Careful, it does not share angle B because angle B is this whole angle, but only this piece of the angle is inside of this triangle. So just be careful with that. Angle A is the angle that is shared between the triangles. So since angle A is shared and angle A is in the bottom right of the first triangle, we need to put it in the same spot, the bottom right, when we're labeling the second triangle. Because if it's shared, it needs to match up in the two triangles. And then that leaves B to be left over. Now, for the last triangle, I'll just outline it in green. The right angle is at D. And this triangle shares angle C with the big triangle. So since angle C was at the top when we redrew the big triangle, it's got to be in the same spot at the top when we redraw this small triangle. And then that leaves angle B to be the leftover one over here. So now we have all of our triangles oriented the same way. And if I wanted to see what sides matched up, it would be really easy to do that because I can easily now see which triangles are in the same spot. And I can also now write a similarity statement if I wanted to, putting all the corresponding parts in order, because now I can see if I'm writing CBA that the order should be BDA for this one, and then the order for this one should be CDB. Let's see some examples of where we need to use the right triangle altitude theorem in order to solve for missing sides. In the diagram below, altitude CD is drawn to the hypotenuse of right triangle ABC. So I see right triangle ABC, and since CD is the hypotenuse drawn to the side, it forms a right angle where it intersects the sides. So now it's asking us which equation can be used to find the length of AC. So basically, it's asking us which proportion correctly puts corresponding sides together. But I don't know that from just looking at this picture. What I have to do in order to see and not make a mistake is redraw the three triangles so that they're facing the same way. I'm going to do it the same way that we just did it before. The big triangle, the right angle is at C. And then it doesn't matter where I put B and A for the first big triangle. It's going to matter for the smaller triangles. Now I'm going to do the medium triangle, and I'm going to outline that one in purple. The medium triangle has a right angle at D, and it shares angle A with the big triangle. Since angle A was on the bottom right of the first triangle, we have to put it in the same spot when we're labeling this triangle. And that leaves C to be the last point by process of elimination. And then we just have one more triangle to go. The right angle is at D. This triangle shares angle B with the big triangle. So angle B was at the top on this triangle. So we have to put it on the top here as well because it matches up. And that leaves C to be the last one by process of elimination there. So we have three similar triangles. And now we can see which of the equations correctly puts corresponding sides together, because now we could see what matches up really easily since everything is oriented the same way. So we have AC, CD. Oh, that doesn't look like it's matching up already. And then we have CD, AD. That doesn't even match up. AC and CD don't match up at all. Nope. Let's check out number 2. CD, AC. Okay, so that's from the same triangle. So now we can see if we have the corresponding sides on another triangle. AC. No, that's in a different spot. Not the answer choice we're looking for. Okay, AC. Oh, sorry. AC and CD. That's from the same triangle. And now let's see if we have what matches up on another triangle. We have CD and BC. No, those are not in the same spots. That one's not good either. So that's going to be answer choice 4, but let's just make sure it works out and that we didn't make a mistake. So we have AB and AC. That's from the same triangle. Let's just see if we have corresponding from another triangle. AC and AD. That looks good to go. So when we do have the triangles drawn the same way, oriented the same way, it makes it so much easier to see what corresponds. I would not have been able to see that with the triangles drawn the original way. The accompanying diagram shows a 24-foot ladder leaning against a building. A steel brace extends from the ladder to the point where the building meets the ground. The brace forms a right angle with the ladder. So basically they're telling us that this is the altitude because it forms right angles with the side of the triangle that it intersects. And it also starts at the vertex point. If the steel brace is connected to the ladder at a point that is 10 feet from the foot of the ladder, which equation can be used to find the length x of the steel brace? So even though this is a really wordy word problem, it's the same picture as we had before with a big right triangle with an altitude drawn to its hypotenuse, creating two smaller right triangles. So we can do the exact same thing that we did before, and we can see which is correctly set up after we redraw the triangles. This one is going to be a little bit trickier to redraw because it doesn't have letters, but we can just give it letters if we want to make our life easier. I'll just call this A, B, C, and D because that's going to really just make my life a lot easier. I'm going to put the right angle in the same spot on all of the pictures. And the first one, I'll just leave as is, A, B, C. And then I will do this triangle next over here, and the right angle is at D, and A is shared between those two triangles. So A is at the top, so A needs to be at the top here. And then that leaves B to be here by process of elimination. For this other one, the right angle is at D, and it shares angle C with the big triangle. So if C was over here, C needs to be in the same spot, and that leaves B by process of elimination. So we have our similar triangles. Let me just transfer the numbers. So AC was 24, and AC is only over there. And then DC is 10. That's over here. And X is DB. We're looking for DB. So DB is over here. And DB is also over here as well. So this becomes a problem because we have the X's on these two triangles, but we're missing a measurement on this triangle over here. But we could get AD because we know that the whole thing is 24. This piece is 10. So if we subtract, this is 14. So that's AD, which is 14. And now we have enough information to make a proportion with these two triangles over here. So one way I could make this proportion is 14 over X from this triangle in the middle is equal to X over 10. And let's see if that's an answer choice. And look at that, that's an answer choice. That's answer choice number 1. So once you set up your triangles facing the same way, you could make your own proportions. You can compare to the answer choice, or it would just be easier if you're going through the answer choices to see what matches up and what corresponds. Okay. In the accompanying diagram of right triangle ABC, altitude BD is drawn to hypotenuse AC. As soon as I see the word altitude, I know it forms right angles with the side that it intersects. And it does say that the triangle ABC was a right triangle, so I know that it has a right angle as well. I'm going to put that in there. In order to determine which statement's true, I'm going to do what we've been doing this whole time, and I'm going to redraw the 3 triangles. Now it's going to get really quick and repetitive because we've been doing it a lot. So I just want to put the right angle in the same spot in all the triangles. It doesn't matter where you put it. The first triangle, the labeling doesn't matter. It's the other 2 that are going to depend on the first one. Let's do the medium one next. The medium one has a right angle at D. It shares angle C with the big triangle, so that needs to be in the same spot, and that leaves B over. For this one over here, the right angle is at D. It shares angle A with the big triangle, so it needs to be in the same spot, and that leaves B by process of elimination. And we have triangles that are similar to each other. Now we can go through the answer choices and we can see which one is a correct statement. So we have AD over AB. So that's from the same triangles. So let's see if we have corresponding parts on the other side. BC, AC. There's no AC there, so maybe it's this BC and this AC. But those don't correspond. That's a different 2 sides than the other triangle. So this one's not going to work. Let's check out answer choice number 2. AD, so this side, over AB. Okay, that's these 2 sides from this triangle, is equal to AB. So far, so good, over AC. That looks good to go. Those correspond. We have our correct answer choice over here. Okay. In the diagram of right triangle KMI, altitude IG is drawn to hypotenuse KM. So we do have 2 right angles that are formed. If KG is 9 and IG is 12, the length of IM is what? So once again, we're going to just redraw all the triangles. Once again, it's going to get very quick and repetitive so that they're all facing the same way. In the big triangle, the letters don't matter. It's the other triangles that are going to matter. Let's do the medium one next. In the medium one, the right angle's at G. It shares M with the big triangle, and that leaves I to be in the last spot. And then for the small triangle, the right angle's at G. it shares K with the big triangle, and that leaves I. And these are all similar to each other. We were told that KG is 9, so I'm going to make sure that I do put that on the triangles. KG is 9, and IG is 12. Be careful because IG appears twice on two triangles, and we need to find the length of IM. So now we can see that it's these two triangles that we have the information about, but they're all similar to each other, so it doesn't matter. And we can make a proportion. I'm just going to do x over 12 equals to 12 over 9. And we can cross multiply. 9x is equal to 144. So now all we'll have to do is divide. So we have 144 divided by 9, and we have 16. Okay. In the next one over here, we have right triangle FGH, and we have the measure of angle GHF is 90. We have altitude HJ is drawn, so it creates 90-degree angles. We have FJ is 16, and we have HG is 15. We need to determine and state the length of JG. And then after that, we'll determine and state the length of HJ. So let's find one first and then the other. So in order to do this, we're going to do the same approach as we've been doing. The only difference is this is a two-part question where we're finding two different things. So let's put the right angles in the same spot. The big triangle, the letters don't matter. It's the other ones that do matter. So let's do the medium-sized one next. The right angle is at J. It shares F with the big triangle, and that leaves H to be in the last spot. And now the small triangle, which also has a right angle at J, it shares G with the big triangle, and that leaves H to be in the last spot over here, and these are all similar to each other. So we have that GH is 15, and there's two spots with GH, so be careful of that. We're looking for GJ, and JF is 16. So now we have a little issue because we don't have two measurements on the same triangle. We're good with this one over here. We have two measurements that we can use from our proportion, but we have measurements on two different triangles, so it's not going to work with setting up a proportion. We need to get another measurement on one of those triangles in order to use it for our proportion. Otherwise, it's not going to happen for us. So a way that we can do that is we can represent this side over here as 16 plus x. And that's going to be a little bit annoying with our calculations, but we can definitely do it. So that's here, 16 plus x. So now we can set up a proportion using these two triangles. So we can do 15 over x, those correspond. And then we can do 16 plus x over 15, those correspond. And once again, the calculations are going to get a little bit annoying because when we multiply this way, we have to do x times 16 plus x. So we are going to have to distribute. And then we're going to have to use some of our Algebra 1 skills because we do have a quadratic here. And that means it's an equation with the highest exponent of 2. And that means you can't just solve regularly. You have to solve by either factoring or using the quadratic formula. I don't really like to use the quadratic formula unless we have to because it's a lot. Most of the time, factoring in geometry works out just fine. So in order to use factoring or even quadratic formula for that matter, your equation does need to be equal to 0. So the reason I'm subtracting 225 from both sides is to just get the equation equal to 0. And then what you're doing is you can make your A times C B chart. You might remember that from Algebra 1. Your A times C is negative 225, and your B is 16. So what you're looking for is you're looking for two numbers that multiply to give you 16, and that add to give you 225. So first, I would think of numbers that multiply to give you negative 225. And then we can verify if they actually add up to give us 16 after that. So 25 goes into it. So that's 25 and 9. Let's see, does that make 16? Let's say we made this one negative and this one positive. 25 minus 9. That does give us 16, so that works out. So sometimes finding the factors can be the most difficult part. So you might need to do some guess and check. So our two factors are 25 and negative 9. So we can factor that to be x plus 25 and x minus 9. So you can actually take each of those separately, if you remember from Algebra 1, and you can solve. So we have x is equal to negative 25. And we have x is equal to positive 9. In geometry, it's really nice because we reject the negative because we're talking about side lengths of a triangle. So we can't have a negative side length of a triangle. So our x value is 9. And we're looking for the length of JG. And luckily, JG is represented as 9. So there we go. Now, after that, we do have to state the length of HJ. That's the second part of this question. So HJ is right over here. I'll label it as Y, and I'll label this as Y over here. Now, you can either set up a proportion again, but now that we already have GJ, if we take a look at this triangle, it's a right triangle, and we have two sides of the right triangle. So you can set up a proportion again, or you can use Pythagorean theorem. Because if you have two sides of a right triangle and you need to find just one more side, the Pythagorean theorem works. So just remember, if you're using the Pythagorean theorem, across from the 90-degree angle is the hypotenuse, and that needs to be plugged in for C. So we have the hypotenuse here, it's 15, so that does need to be plugged in for C. And then one of the legs is 9, we just found that, that's JG, we found it before. And then the other leg is what we're looking for. You can leave it as b squared. We just called it y here, so I'm calling it y. And then we can solve. We have 81 plus y squared equals to 225. Let me subtract 81. And we have 144. And then we could take the square root of both sides. And we have y is equal to 12. And y represents the length of JG, so the length of JG is 12. And there we have it. Moving along. Over here, we have right triangle ABC, and CD is the altitude to hypotenuse AB. So CD forms right angles where it intersects AB. If CD is 6 and the ratio of AD to AB is 1 to 5, determine and state the length of BD. So whenever you have a ratio and you want to represent it algebraically, you can represent the 1 part as 1x, or just x, and the 5 part as 5x. So AD is written first, so it's the 1 part. So I can represent that as 1x, or just x. And then AB is the second part of the ratio because it's written second. So we can represent that as 5x. So that means this has to be 4x. And we're finding the length of BD. Let's redraw our triangles so that they're all facing the same way. The big triangle, I'm going to label as BCA. And then let's do the medium-sized triangle next. The medium-sized triangle has a right angle at D. It shares B with the big triangle. And then that leaves C. by process of elimination. And then finally, the small triangle has a right angle at D. It shares A with the big triangle, and that leaves C by process of elimination as well. So we know that CD is 6. Let me just label that and be careful because it's in 2 spots. And we need to find BD. BD is represented as 4x. Oh, wait. Let's fix this. So if there's the 1 part and the 5 part, that means together there are 6 parts in total. So let me change this slightly. Let's do 6x. And let's make this over here 5x. And that makes more sense because now the 5x and the 1x part makes the 6x in total. Okay, so we need to find DB. DB, I'm going to represent as 5x. And we also have AD, which is 1x. So now we can make a proportion. 5x over 6 equals to 6 over x. So we have 5x squared equals to 36.